Let me ask you something, and I want you to actually try to answer it before I say another word. You're sitting down right now, probably in a chair, and the chair is holding you up. You're not falling. You're just sitting there, perfectly content, supported by a few pieces of wood, or metal, or plastic. Now, why? I'm serious. Why does the chair hold you up? I'll bet the answer that popped into your head was something like, well, the chair is solid, and I'm solid, and two solid things can't be in the same place, so the chair stops me. The chair is hard. It's made of stuff, and the stuff is in the way. That's a perfectly reasonable answer. It's also, when you really start poking at it, completely mysterious. Because if I asked you what solid actually means, what hard actually means, what it means for two things to be in the way of each other, you'd find out very quickly that you don't know. Nobody knew for a long time. And the real answer, the honest answer, is one of the strangest, most beautiful facts in all of physics. It has almost nothing to do with what you think it does. So let's take this apart slowly, one layer at a time. And I promise you, by the time we hit the bottom of this, you will never sit in a chair the same way again. Let's start with the easy layer. The chair is made of atoms. You are made of atoms. When you sit, your atoms come down toward the chair's atoms, and somewhere something says, that's far enough. The chair pushes up on you exactly as hard as gravity pulls you down, and you balance and you sit. Fine. So far, this is the kind of thing you could read anywhere. But now I want to look closer. I want to look at one atom. Just one. And I want to ask, what is that atom actually like inside? Here's where the trouble starts. You probably picture an atom as a little solid ball, a tiny marble, maybe a fuzzy marble. And if it's a solid little marble, then sure, a pile of marbles is solid, and a chair made of marbles is hard, and we're done. But an atom is not a solid little marble, not even close. In the middle of an atom, there's a nucleus. That's where almost all the mass is. The protons, the neutrons, all bunched together. And around that nucleus, somewhere, there are electrons. Now, how big is the nucleus compared to the whole atom? Let me give you the picture that finally made this real to me. Imagine you blow up a single atom until it's the size of a great cathedral, a big one. Soaring ceilings, the whole thing. You walk inside this cathedral, this enormous stone space, and you look for the nucleus, the thing that holds nearly all the weight of the atom. And do you know what you find? Floating somewhere in the middle of all that vast empty air? A fly. One fly. Maybe a grain of salt. That's the nucleus. That's the dense, heavy heart of the atom. And compared to the whole atom, it is smaller than an insect in a cathedral. So where's everything else? Where's the rest of the atom? It's empty. It is almost entirely, staggeringly empty. The electrons are out there somewhere near the walls, but they're tiny too, and between the fly in the middle and the walls of the cathedral there is nothing. No stuff. No marble. Empty space. Now stop and feel how strange this is. Your hand is made of these things. Cathedrals of emptiness with a fly in the middle. Your chair is made of these things too. So when you put your hand on the table, you are pressing one collection of mostly empty space against another collection of mostly empty space. By the numbers, by the sheer geometry of it, your hand should pass straight through the table like a ghost through a wall. There's practically nothing there to stop it. The stuff is a rounding error. The atom is basically vacuum with a rumor of matter in it. And yet your hand does not go through the table. You can pound on the table, and it hurts, and the table wins. Two clouds of almost nothing slam into each other and refuse, absolutely refuse, to overlap. So that's our first surprise, and I want you to sit in it for a second. The solidity of the world is not because the world is full. The world is mostly empty. Solidity is something else. Solidity is a kind of trick. The question is, what's the trick? All right. Let's add the next layer. If it's not stuff getting in the way of stuff, then maybe it's forces, and that's a much better instinct. Because we know about a force that lives inside atoms, electricity. The nucleus has a positive charge from the protons. The electrons have negative charge. And we know the rule, the famous rule from when you were a kid playing with magnets and combs and bits of paper. Likes repel, opposites attract. Two negative charges push each other away. So here's the natural next guess. The outside of every atom is draped in electrons. Negative charge on the outside. When your hand comes down toward the table, the electrons on the bottom of your hand meet the electrons on the top of the table. And negative meets negative, and they shove each other apart. The table pushes back on you with electric force. Your hand never actually touches the table, in the deepest sense. The electron clouds just refuse to merge because they repel. This is a good answer. It's the answer a lot of clever people will give you, and it's partly right. There really is electric repulsion between the electrons, and it really is electromagnetic forces in the end that you feel pushing back when you lean on something. So please don't throw this idea away. Hold on to it. But I have to tell you as gently as I can that it is not the bottom of the story. It's not even close to the bottom. And here's how we know. Let me ask you a sneaky question. If two negative charges just push each other apart, then why don't the electrons inside a single atom push themselves apart? You've got a whole crowd of electrons in there, all negative, all repelling each other, and they don't fly off. They stay put. And more than that, why don't all those electrons just fall down onto the nucleus? The nucleus is positive. The electrons are negative. Opposites attract, remember? The nucleus should be pulling those electrons straight in, like a drain pulling water. By the old electric picture, every electron should spiral down and crash into the nucleus, and the whole atom should collapse into a tiny dense speck in about the blink of an eye. But it doesn't. Atoms don't collapse. They sit there, full-sized, cathedral-sized, holding their shape for billions of years. Something is holding the electrons out, away from the nucleus, keeping the atom big and puffy and mostly empty. And whatever that something is, it is fighting against the electric attraction, not because of it. So now we've got a real mystery on our hands. The electric force, by itself, wants to crush the atom. The thing keeping the atom open, keeping it large, keeping it occupying space at all, must be something other than electricity. And that same something, I'm going to argue, is the real reason your chair holds you up. Let me take you down to the next layer. This is where we leave the old world behind, and we step into the strange one. To understand why the atom doesn't collapse, you have to understand that an electron is not a little marble orbiting the nucleus like a planet around the sun. That picture is wrong. It's a nice picture, it got us started, but it's wrong. The electron does not have a definite spot. It is spread out. It's a kind of smear, a cloud of possibility around the nucleus, and the rules that govern that cloud are the rules of quantum mechanics. And here is the first deep thing. There's a principle that says you cannot pin a tiny thing down too tightly. The more you try to squeeze an electron into a small space, the more wildly it has to move. If you confine it, it fights back. Push it into a smaller and smaller box, and it gets more and more frantic, more and more energetic, like a bee in a shrinking jar that buzzes harder the more you crowd it. So when the electric force tries to pull the electron all the way down into the nucleus, into that tiny space, the electron resists, because being crammed into a tiny space costs an enormous amount of energy. The atom settles at a size where these two things balance, the pull inward and the electron's refusal to be squeezed. That balance, that standoff, is the size of the atom. That's why your atom is cathedral-sized and not fly-sized. Good. So now we understand why one atom stays big. But that's still not enough to explain your chair. Because here's the thing. Even if every atom is big and puffy, you could still imagine pushing two atoms together so their clouds overlap, so they share the same space. The clouds are soft, they're fuzzy. Why can't they just blend? like two clouds of smoke drifting into each other and merging into one bigger cloud. If atoms blended like smoke, the world would be a catastrophe. You'd push your hand toward the table and the atoms would just merge, pass through, blend together. Everything would sink into everything. There'd be no solidity at all. The whole universe would collapse into a kind of sludge. So why don't electron clouds merge like smoke? What stops two atoms from sharing the same space? And now, finally, we arrive at the strangest thing of all. The thing this whole lecture has been climbing toward. It's a rule about electrons that has no everyday explanation, no picture from ordinary life that fully captures it. A rule that is simply how nature is built at the deepest level. It's called the exclusion principle. A fellow named Wolfgang Pauli figured it out back in 1925, and it goes like this. No two electrons can ever be in the same state at the same time. Let me say what that means, because it sounds like nothing and it's actually everything. Every electron in a system has a sort of complete description, where it tends to be, how it's moving, which way it's spinning, the whole package. And Pauli's rule says that no two electrons are ever allowed to have the exact same complete package. They can't both be in the same place, doing the same thing in the same way. Each electron must have its own state, its own slot. And once a slot is taken, it's taken. No other electron may enter it. Period. Not because they repel, not because of any force pushing them apart, simply because nature forbids it. Two electrons in the same state is not allowed. It's a law deeper than any force. Now I want you to feel what this does. Picture the electrons as people, and the states as chairs in a theater. Electric repulsion would be like the people not wanting to sit too close because they don't like each other's company. That's a force, it's a preference. You could overcome it if you pushed hard enough. But Pauli's rule is not like that at all. Pauli's rule is that each chair physically holds exactly one person, and there is no possibility, none, of a second person in that chair. The chairs are one-person chairs by the unbreakable law of the theater. If you want to seat more people, you must use more chairs. Higher up, further back, there is no cramming. So now watch what happens when you push two atoms together. You bring your hand down toward the table. The electrons in your hand have their states, their slots, their chairs, all the low comfortable ones near the front, all filled. The electrons in the table have theirs too, all their low chairs filled. And now you try to push them into the same region of space. You're trying to make your electrons and the table's electrons occupy the same slots, sit in the same chairs. And Pauli says no. There are no free chairs down low. They're all taken. So if you want to force these electrons into the same space, the only place for them to go is up, into higher states, higher energy. And higher energy means it costs you. It costs an absolutely tremendous amount of energy to promote all those electrons up into empty states, just so two pieces of matter can share the same space. Squeeze a little, and the cost shoots up. Squeeze more, and it shoots up faster than you can believe. The matter pushes back. Not because the charges repel, though they do a bit. It pushes back because you are asking electrons to do the one thing in the universe they are absolutely forbidden to do, which is share a state, and the price of even getting close to that is enormous. That push, that refusal, that is what you feel when you lean on the table. That is what holds you in your chair. It is not stuff blocking stuff. It is not even mainly electric repulsion. It is the exclusion principle. It is electrons standing on their absolute right to their own private state, and the universe charging you a fortune in energy every time you try to crowd them. Your chair holds you up because electrons refuse to be in the same place, in the same way, at the same time. The hardness of the world, the solidity of every object you have ever touched, the floor under your feet, the cup in your hand, the bone in your own body, all of it, the entire firmness of the material world comes from this one quiet, stubborn rule that no two electrons may share a state. Isn't that something? You sat down expecting wood to stop you, and instead you were stopped by one of the deepest laws of quantum mechanics. Now let me be honest with you, because I always try to be honest about where the edges of our knowledge are. When physicists argue carefully about exactly what you feel when you press on a table, they'll point out that the forces between atoms really are electromagnetic. The actual push, the actual transfer of force, comes through electric and magnetic interactions. That part is true. But here's the subtle, crucial point. The reason that push doesn't just collapse, the reason matter takes up space at all, the reason 2 blocks of metal occupy twice the volume of 1 block instead of all merging down into a single tiny point, that comes from Pauli. Without the exclusion principle, you could prove, with real mathematics, that ordinary matter would implode. It would crush down into something unimaginably dense. The world would not be able to hold its shape. So when I say your chair holds you up because of the exclusion principle, what I mean is this. The electricity does the pushing, but Pauli is the reason there's anything left to push on. Pauli is why matter is fluffy instead of crushed. And that fluffiness, that refusal to collapse, is the solidity you feel. Let me show you just how serious this is. Let me show you what happens when Pauli's refusal gets pushed to the limit. Because there are places in the universe where matter gets squeezed so hard that this whole story is on the line. Think about a star. A big ball of gas, burning, holding itself up against its own gravity by the pressure of all that heat. For most of a star's life, that works fine. The heat pushes out, gravity pulls in, they balance. But eventually the star runs out of fuel, the fire goes out. And now there's nothing to push back against gravity. The star starts to collapse under its own weight, crushing inward. Smaller and smaller. What stops it? For a lot of stars, what stops it is exactly the principle we've been talking about. As the star collapses, the electrons get crowded closer and closer together. And remember, Pauli says they cannot share states. So as you squeeze them, they're forced into higher and higher energy states, just like when you pressed your hand on the table. The electrons fight back with a pressure that has nothing to do with heat and nothing to do with electric repulsion. It's pure exclusion. We call it degeneracy pressure. And for a dying star of the right size, that pressure, the simple refusal of electrons to share a state, is strong enough to hold up an entire collapsing star. The star settles into a dense, faintly glowing ember about the size of a small planet but with the mass of the sun. We call it a white dwarf. A whole dead star, held up against the crush of its own gravity by nothing but the same rule that holds you in your chair. But here's the part that gives me chills. There's a limit. If the dying star is heavy enough, gravity gets so strong that even Pauli's rule isn't enough. Gravity wins. It overpowers the electrons' refusal, crushes them right into the protons, and the whole star collapses further into something even denser, a neutron star, where now it's a different set of particles standing on the same principle, refusing to share states, holding the line. And if the star is heavier still, even that fails, and there is nothing left to stop the collapse, and you get a black hole, a place where matter has finally lost the fight to take up space at all. So this rule, this same little rule about electrons that holds you in your chair right now, is the very thing that decides the fate of stars. Whether a star ends as a quiet ember or collapses into a hole in space comes down to whether the exclusion principle can hold against gravity. The reason your coffee cup is solid and the reason a dead star doesn't vanish into a point are the same reason. It's the same law. Sitting in your chair, you are leaning on the very thing that holds up the corpses of stars. Let me pull back and look at the whole picture now, because I think it's worth seeing all at once. You sat down, the simplest thing in the world, and we asked why the chair holds you up. And the first answer was, because it's solid, it's full of stuff. And we found out that's wrong. The chair is mostly empty, cathedrals with flies in them. Then we said, well, it must be electric repulsion, electrons pushing on electrons. And that was closer, but we found out it's not the heart of it. because electricity alone would crush the atom, not hold it open. And then we went down to the strange floor of the world and found the real reason, the exclusion principle. Electrons refusing, absolutely and without exception, to occupy the same state. That refusal is what gives every atom its size. That refusal is what stops two objects from merging. That refusal is the hardness of the world. And that same refusal, scaled up to the cosmos, holds up dying stars against the weight of their own gravity until, at the very limit, even it gives way. So the next time you sit down, I want you to think about what's really happening. You are not being held up by wood. You are being held up by a law that says every electron gets its own state and no one may ever take it. Trillions upon trillions of electrons in your chair, every single one of them clutching its own private slot in reality, refusing to let your electrons in. And in that refusal, multiplied across all those countless particles, you find something that feels almost solid enough to sit on. It isn't the wood. It was never really the wood. It's the rule. There's one more thought I want to leave you with, and it's the one I can't quite put down myself. We started this whole thing by noticing that matter is mostly empty space, a fly in a cathedral. By rights, the world should be a thin, ghostly, insubstantial place that we ought to be able to walk straight through. And the only reason that the world feels solid and real and trustworthy under our hands and our feet, the only reason you can build a chair and trust it to hold you, is a principle that we cannot see, cannot picture, cannot derive from anything more familiar. A bare law of nature that says some things simply cannot be the same. The entire solidity of your life is built on a rule about what is not allowed. So here's what I'd love to hear from you. After sitting with all this, what's the most solid, dependable thing in your life that you now realize is really being held together by something invisible? Tell me what you came up with.